modern life could not exist if it were not for electricity and electronics. The history of electricity starts more than 2,000 years ago, with the Greek philosopher Thales being the earliest known researcher into electricity. But it was Alessandro Volta who created the most common DC power source, the battery. For this invention the unit volt was named after him. A circuit is a closed loop that electrons can travel. A source of electricity, such as a battery, provides electrical energy to the circuit. Unless the circuit is complete, that is, making a full circle back to the electrical source, no electrons will move. A closed circuit is when a continuity for current flow is provided, and an open circuit is when a flow for current is not allowed. Voltage is the pressure from an electrical circuit's power source that pushes charged electrons, current, through a conducting loop, enabling them to do work such as illuminating a light. Current is a flow of electrical charge carriers, usually electrons or electron-deficient atoms. Resistance is a measure of the opposition to current flow in an electrical circuit. It is measured in ohm and symbolized by the Greek letter omega. Conductors, materials that offer very little resistance where electrons can move easily. Examples: silver, copper, gold, and aluminum. Insulators, materials that present high resistance and restrict the flow of electrons. Examples: rubber, paper, glass, wood, and plastic. Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Introducing the constant of proportionality, the resistance, one arrives at the usual mathematical equation that describes this relationship. Supposed, a 5 ohm resistor is supplied with a 12-volt battery. What is the current flowing to the resistor? From the problem, we define the resistance as equal to 5 ohms and the voltage equal to 12 volts. Applying Ohm's law as 12 divided by 5 will give us the current equal to 2.4 amperes. A series circuit comprises a path along which the whole current flows through each component. The figure shows the resistors to be connected in series, giving a single path for the current to flow in the circuit. It is also a characteristic of a series circuit that the current flowing to each resistor to be equal in the sum of voltage drop in each resistor to be equal to the total voltage supplying the circuit. From the characteristics of a series circuit, being the sum of each voltage drop equal to the voltage source, we can derive the total resistance in a series circuit to be equal to the sum of each resistance. A parallel circuit offers 2 or more paths for the current to flow. The figure shows the resistors connected in parallel, offering 3 paths for the current to flow. It is a characteristic of the parallel circuit that the voltage drop in each resistor to be equal to the voltage connected across the resistors. Also, the sum of the current flowing in each resistor is equal to the current provided by the source. From the characteristics of a parallel circuit, being the sum of each current equal to the current source, we can derive the total resistance in a parallel circuit to be equal to the inverse sum of the inverse of each resistance. Kirchhoff's current law, often shortened to KCL, states that the algebraic sum of all currents entering and exiting a node must equal 0. This law is used to describe how a charge enters and leaves a wire junction point or node on a wire. In the figure, It showed that the current leaving the junction is equal to the sum of the currents entering the junction. Thus, if we assume that the current leaving the junction to algebraically negative and the current entering the junction to be algebraically positive, the algebraic sum of the current leaving and entering the junction to be equal to 0. Kirchhoff's voltage law, often shortened to KVL, states that the algebraic sum of all voltages is equal to 0. In the figure, if we assume the polarity of the voltage to be the exit of the loop, then we can say positive voltages to the voltage source and negative voltages to each voltage drop. Therefore the total voltage minus the voltage drop at resistance number 1, minus the voltage drop at resistance number 2, minus the voltage drop at resistance number 3, will be equal to 0. The voltage divider formula states, the ratio of individual resistance to total resistance is the same as the ratio of individual voltage drop to the total supply voltage in a voltage divider circuit. The current divider formula states, the ratio of total resistance to individual resistance is the same ratio as the individual branch current to the total current. Power is a measure of how much work can be performed in a given amount of time. Work is generally defined in terms of the lifting of weight against the pull of gravity. The heavier the weight and/or the higher it is lifted, the more work has been done. Power is a measure of how rapidly a standard amount of work is done. Power is measured in watt. Power as a function in joule states the amount of work done in a period of time, therefore 1 watt is equal to 1 joule of work done in 1 second, joule per second. Power as a function of voltage and current states that the power is equal to the product of voltage and current. Also, considering the characteristics of a parallel circuit as the total current is equal to the sum of individual branch current, and the characteristics of a series circuit as the total voltage source is equal to the individual voltage drop of each component, we see that the total power given by the source is equal to the sum of power dissipated in each component in the circuit. Let's solve an example. In the given figure, let us solve for the total power and the individual power dissipated in each resistor. We will approach this problem by solving each unknown first. To begin, we need to solve for the total resistance, then solve for the total current flowing through the circuit. From the we can solve for the individual voltage drop 1 in each resistor, then we can solve for the total power and the individual power dissipated in each resistor. Now try solving this problem on your own. Have you got the right answer?